Hello, everyone. I'm Salam Thabit, a PhD student at American University of Beirut, and I'm going to present to you my work, Adaptive Mobile Diminished Reality Framework for 3D Visual Privacy. The presentation is organized as follows. First, I will provide a brief introduction and a glimpse into related work, followed by my systems design, implementation details, and results, before ending with a small demo and a conclusion. So let's get started. We live in a digital world where we expose too much of our personal lives. The amount of visual data collected is proliferating by the second. Emerging visual data collecting technologies that have gained a surge in popularity recently are immersive technologies, augmented reality, virtual reality, and mixed reality. The increasing pervasiveness of these technologies, specifically AR and MR applications, poses privacy risks, especially since AR cameras are continually capturing information about user surroundings, including people and personal places. A typical risky setting for these application environments might include a credit card placed on a table at home, a secret contract on an office desk, or an industrial robot in the background. Therefore, there is a need to implement seamless but selective sharing capabilities in MR systems. So, to mitigate the risk of private content inadvertently leaking in an MR user's environment, we propose a mobile, privacy-preserving diminished reality framework that enables users to obfuscate their most sensitive objects on the fly during a live MR feed to obfuscate 3D objects that adapts to motion. Most previous privacy-preserving frameworks are focused on providing face de-identification or individual anonymization. However, faces are not the only sources of privacy-sensitive information, and anonymization of the user is not applicable in all cases, especially in applications where the identity of the individual needs to be revealed, like video conferencing apps. Moreover, existing AR privacy frameworks either focus on identifying and obfuscating specific types of objects, struggle with maintaining acceptable performance during camera motion, or they are not tailored for 3D environments, always assuming the privacy-sensitive information is in the background. The few works that provide 3D privacy follow the least privilege paradigm, where only the minimal information required to perform a certain task is released. Our framework provides the user the ability to select and obfuscate any private object and focuses on preserving 3D visual privacy in a 3D environment where the camera is moving freely. And the pipeline of our DR system consists of the following stages. So first we have object selection, where the selection criterion is user-defined, and the platform enables the user to place a 3D visual primitive shape, like a cube, that encloses the 3D world, the real-world private object from all sides. The region of interest, or ROI, which we will obfuscate, is then extracted in every frame as the convex hull of the placed 3D virtual object. And the next step is obfuscation, by either blurring or inpainting the extracted ROI in every frame. To enhance privacy guarantees as the user moves freely in the 3D environment, we apply two algorithms. We presented the snapback algorithm in our previous work to fully enclose the private object from all sides and prevent an accidental revelation of the private object due to the different perspectives during 3D rotation motion around it. However, it had limitations when dealing with sudden or fast movements. And in this work, we addressed this limitation and we proposed the adaptive algorithm on top of our previous DR system that monitors the camera motion and adapts the size of the obfuscation area according to the speed and acceleration of the camera in real time to enhance privacy guarantees even during fast and sudden movements. We will explain the two algorithms next. So if the virtual object is placed or moved around in a way that does not enclose the sensitive object entirely, a snapback of the virtual object is performed, which automatically positions and scales it accordingly, so that the entire object is enclosed and obfuscated. The snapback procedure works by the following steps, which are also demonstrated on the side. First, we run any object detection model like YOLO. We select the bounding box of the object closest to the obfuscation. Then we snap the obfuscation back to its correct place and size, which is enclosing the selected bounding box. In subsequent frames, we keep tracking the bounding box and we adjust the position and scale of our object accordingly. As for the adaptive algorithm, also demonstrated on the side, it monitors and reacts to the following parameters, which mainly affect the detection and tracking of private objects and consequently affect the achieved level of privacy. First, we have the speed and acceleration. So if the speed or acceleration of motion exceed a certain threshold, the adaptive algorithm increases the area of obfuscation. These help indicate when the movement is sharp or when an abrupt change of direction occurs. And it also monitors the object detection of the private object. So if the object detector fails to detect the private object in a given frame, the area of obfuscation is increased aggressively, since the private object can be anywhere and not necessarily overlap with the virtual object, which risks extreme exposure of the private object. And finally, we also monitor plane tracking because if the running AR subsystem fails to properly track the plane where the private and virtual objects are anchored in a given frame, the area of obfuscation is also increased aggressively, since the private object can be anywhere relative to the inaccurately detected plane in the current frame, and not necessarily overlap with the virtual object, which also risks extreme exposure of the private object. If none of the monitored parameters sense a privacy failure, the area of obfuscation is gradually reverted to its original size. As for the output action of the adaptive algorithm, it's one of the following. So it's either multiplicative increase or additive decrease, followed by a weighted average. For the multiplicative increase, the area of the obfuscation is increased by increasing the scale of the placed virtual object that covers the private object. To minimize the risk of exposing any part of the private object during rapid movement, the scale is increased sharply by multiplying it by a factor, beta, that is greater than 1 in each frame. And the scale of aggressiveness of the adaptive algorithm is controlled by beta. And the additive decrease, in the additive decrease, the area of obfuscation is decreased by decreasing the scale of the placed virtual object that covers the private object. Since protecting privacy is the adaptive method's main aim, the scale is decreased slowly by decreasing a small factor, gamma, from it in every frame. And finally, to ensure a smooth change in the blurred area for improved human perception, the updated scale is a weighted average of the scale in the previous frame and the new scale that is computed by the adaptive algorithm using the multiplicative increase, additive decrease. As for our implementation details, we used Unity and AR Foundation. We also used OpenCV for Unity plugin for OpenCV functions. And the application can be built for any platform that supports AR Foundation. But it was tested on the Android device Infinix Note 11 Pro. Now, before showing the results of our algorithm, I just want to point out how we are measuring privacy. So the privacy measure is defined as the percentage of the private object's area that is contained within our obfuscation mask. So if the mask area and the private area are as shown in the figure, their intersection in yellow represents our achieved privacy percentage. These plots show how the snapback privacy, the adaptive privacy, and mask sizes vary with instantaneous acceleration and speed for one of the sample runs, where the camera was moving slowly at certain frames and fast at other frames around a private object. The plots clearly show how the adaptive mask size increases sharply or multiplicatively when any of the aforementioned speed and acceleration thresholds are bypassed, and how it decreases slowly or additively when none of the thresholds are exceeded. While the snapback privacy levels drop significantly to reach 0 at high speeds and high accelerations after frame 120, the adaptive algorithm reacts to the drastic increase in the camera movement and increases the obfuscation area sharply to maintain a perfect privacy level at 100%. Once the motion becomes slow again, the acceleration and speed drop below their thresholds and the adaptive mask size drops slowly. The privacy results of our experiments are averaged, and the privacy failure count for two privacy thresholds, 95% and 99%, are aggregated for every set of 20 experiments for translation motion and 15 experiments for rotational motion. For three types of objects, a bottle, a mug, and a banana, during slow and fast motion. We showed these aggregate results in the first two tables, and it is evident from the privacy failure count results for both thresholds that the adaptive method has a significant advantage over the snapback method, especially during fast motion. We summarized the overall average improvement of privacy levels during slow and fast motions of the adaptive method versus snapback in the third table. The adaptive technique greatly enhances privacy in all cases. When the snapback method fails to obfuscate more than 95% of the private object, more than 18% of the time, the adaptive method significantly reduces the failures to less than 0.2%. Now we will show a demo for rotational motion. We show the original video, the one where snapback only is applied, and one where the adaptive method is applied. When the speed increases, the adaptive increases the scale quickly and successfully blurs the entire mug, even when the snapback algorithm fails. When we slow down over here, the adaptive scale slowly decreases back to its initial size. And then we increase our speed again. The adaptive increases, snapback fails. However, adaptive successfully blurs the whole mug throughout the entire run, even during fast and sharp movements. Similarly, we show a demo for translation motion. The adaptive method also quickly increases the scale as we increase the speed and sharpness of the movement to prevent privacy failures that happen with the snapback method. Once we slow down, it also decreases back to its original size. So for our conclusion, we presented an on-device real-time 3D visual privacy preserving DR system that adapts to fast motion patterns through an adaptive algorithm. We demonstrated our framework's ability to enhance privacy guarantees and reduce the average frequency of privacy failures from over 18% of the time to less than 1% of the time as compared to state-of-the-art. However, since covering the entire screen can also maintain perfect privacy in real time, we need a way to distinguish our method from such drastic measures, as we are only covering the most critical parts of the screen. This highlights the need for defining a suitable privacy utility trade-off for our particular use case. We aim to define utility and measure the privacy utility trade-off in our future work. We also aim to extend our implementation to obfuscate dynamic objects. Thank you for listening. If you have any questions, I'll be happy to answer.